Welcome to this webinar entitled Magnetic Gears for Electric Propulsion. In this webinar, we will cover from problem to practical solutions, and we will have a live demo on simulation. To have an overview on this webinar, first we will have a brief introduction about why magnetic gears matter compared to the traditional mechanical gearboxes. And we will investigate how actually magnetic gears work. Next, we are going to have examples about magnetic gears applications in the real industrial use. In the next part, we will do a live demo simulation in EMWorks EMAG, the electromagnetic simulation software, to see the magnetic gear performance and see the user-friendly workflow of the software. During the webinar, if you have any questions, feel free to type them in the chat box and I will answer them all after the live demo in the question and answer part. Basically, the mechanical gears until now are widely used in industry because they are already well established and well developed, but they are prone to some serious problems. First of all, they come with friction and wear, which is going to reduce the efficiency of the drivetrain over the time. And they need continuous lubrication and maintenance due to the physical operation and physical contact between two rotors. And because of this physical contact between teeth, we are going to always have noise and vibration, which makes it undesirable for some applications, and also it's going to limit our design flexibility. So typically mechanical gears lose 5 to 10% of energy in the drivetrain over time. All these mentioned problems made researchers to come up with a new design and new structure that eliminates this physical contact operation. Almost like 25 years ago in 2000, coaxial magnetic gear was first proposed, and after that researchers tried to improve its performance and compare it with mechanical gearboxes. In magnetic gears, unlike the mechanical gearboxes, the torque transmission is based on the magnetic field instead of mechanical teeth. So, since physical contact is eliminated, the wear and friction is minimal and we have a quiet operation. Another interesting characteristics about magnetic gears is that they have intrinsic and built-in overload protection. Since the two rotors are separated from each other, if we have any fault on the load side, it's not going to be transmitted to the prime mover or the electric motor. So this magnetic slip prevents the physical damage to the motor shaft. All in all, the magnetic coupling ensures the torque transfer even in harsh or lubricated-free environments, especially for aerospace or satellite applications. The performance of the magnetic gear is based on the interaction between flux density harmonics. In this slide, we have two figures. In the left slide, we have the highest speed in a rotor which has a lower number of pole pairs. This rotor, when it creates a flux density distribution, these flux lines pass through the ferromagnetic pole pieces as shown in this figure. And these ferromagnetic pole pieces actually they modulate the flux density. And the modulated flux density has the amplified harmonics corresponding to the flux density created by the other rotor. So due to the interaction between harmonics, the torque is going to be transmitted between two rotors. The same story is going to happen for the outer rotor, the low speed. As if we see the right figure in this low speed rotor also creates a flux density distribution, and this flux, after being modulated, by the ferromagnetic pole pieces, it's going to have a flux density corresponding with the same harmony to the flux density of the inner rotor. So basically, the ferromagnetic modulators distort and redirect the magnetic flux to provide the magnetic interaction and torque transmission. After the proposal of magnetic gear, researchers tried to come up with new structures and novel configurations to improve the overall performance. The simplest and most basic structure is the surface-mounted PM, in which the permanent magnets are simply mounted on the surface of the yoke. Magnets are mounted on the rotor with glue or mechanical approaches that can stick the magnets on the surface of the yoke. This structure is simple, it has low manufacturing cost, and it's robust. So it's usually ideal for any general use. After that, hullback structure is proposed, in which instead of using whole piece of magnet, we divide it to permanent magnets in several pieces with different magnetization directions. So this technique provides a flux density more sinusoidal in the air gap, which results in higher efficiency and low cogging torque in the operation of the magnetic gear. So since the quality of torque transmission is highly improved in this structure is very appropriate for precision systems. Another interesting structure is the flux focusing or spoke type, in which the permanent magnets are inserted inside the rotor yoke, and due to the flux focusing effect, they generate a flux density in the air gap, which provides a higher torque density. And also, this structure is mechanically reliable and robust because in this structure, the permanent magnets are buried inside the rotor yoke instead of mounting on it. They are buried inside the rotor so they can be more reliable in high-speed drive applications. Establishing the performance of magnetic gears, we can incorporate magnetic gears in the real life and real practical usages. For example, the most famous application of magnetic gears is in the EV drivetrains or electric vehicle drivetrains. We can insert the magnetic gear in the drivetrains with two typical methods: axial integration or radial integration. In the axial integration, the electric motor is axially coupled to the magnetic gear, like the rotor of the electric motor is connected to the inner rotor of the magnetic gear and transmits the torque speed levels through the common shaft. On the other hand, we have the radial integration, in which the electric motor and magnetic gears are radially coupled in the same housing and same enclosure, which is also called pseudo-direct drive motor. These structures provide a higher torque density at low speed for the wheels of the electric vehicle. And since they have natural overload protection, they are very attractive for these applications. Another application of magnetic gears is in wind turbine. In traditional wind turbines, the mechanical gearboxes are often the weak point, so they create noise, vibration, and frequent maintenance issue, which not only increase the operational cost but also reduce system uptime. Magnetic gears, on the other hand, provide an elegant alternative because there are no physical contact between rotating parts. Actually, they operate quietly and require almost no lubrication or maintenance. This will drastically reduce the mechanical failure and lower acoustic emissions, which is particularly important for offshore and urban wind farms. Another major benefit is reliability. By replacing the conventional gearbox with a magnetic gear or integrating it directly with the generator, we can extend the turbine's life and ensure more consistent energy output over time. In this slide, you can see several integration concepts. On the left hand, the DFIG axially coupled with the magnetic gear shows how magnetic gears can interface directly with double-fed induction generators. In the middle, permanent magnet generator or synchronous generator coupled with magnetic gear achieves higher efficiency and simpler power conversion. And the picture on the right, we see a radial coupled configuration of our direct drive system, which high torque density at low speed, ideal for large scale turbines. Water environments, mechanability, critical gear with the metal generation and maintenance all are undesirable for and research submarines. This is where magnetic gears truly shine. So because the torque is transmitted through magnetic field instead of direct contact, the system operates smoothly and quietly, almost eliminating vibration and mechanical wear. This makes them ideal for naval application where acoustic stealth is essential. Another advantage is that magnetic gears are completely sealed, meaning they can operate reliably in salt water without the need for lubrication. This not only enhances safety and longevity, but also makes them perfect choice for hybrid or fully electrical marine propulsion systems. As shown in the diagram, here we have a magnetic gear direct drive machine design for hybrid ship propulsion. The prime mover, which could be a diesel engine or combustion engine, drives the system through a clutch and the magnetic gear assembly transferring torque to the propeller. The windings on the stator and the magnetic coupling between the inner and outer rotor ensure a smooth torque transmission with minimal noise. And also these windings can provide the electrical energy required for the electric loads in the other parts of the ship. And another field which magnetic gears excel is in the robotic and actuators. In these fields, even the smallest vibration or mechanical backlash can affect the performance. So magnetic gears provide an elegant solution by transmitting torque smoothly and without contact, delivering a high precision and quiet motion, which is ideal for satellite positioning systems or aircraft actuators and robotic joints. These applications require extremely accurate control. So, for robotics, magnetic gears bring another key, which is the safety. Because there is no mechanical contact, they naturally limit torque in the event of unexpected collisions. So this makes them perfect for collaborative robots, or we call them cobots, that work safely alongside humans on assembly lines or research environments. They also have low maintenance requirement, the lightweight design. Both are essential for aerospace systems where every gram and every hour of maintenance counts. So at the bottom, you can see an example of how a magnetic gear-based robotic actuator works. Power flows from DC bus and inverter to a high-speed motor, which is usually a BLDC motor because we want them to be small in robotic application. And then this motor drives the magnetic gearbox, and the gearbox provides a smooth torque amplification to the actuator. Now we will have a live demo of the software workflow to simulate a sample of a magnetic gearbox. In this live demo, we are going to see the workflow of simulation this magnetic gear. We will start step by step from importing the geometry to setting up different properties like material, boundary, excitation, and mesh settings. At the end, we will extract the results like magnetic field design or tabular results like transfer. Let's start from beginning by creating a new project inside the project manager window. One of the features of EMWorks software from EMWorks is you can handle different projects inside the project tree, and in each project you can have several designs. To show this multi-project, multi-design management, I will create a new project here, a standard project, and save the name. And you will see it is asking for saving the previous project. Now we have two different files inside the project tree that we can choose to work with. The first step of simulation is creating the design. You have to right-click on the design and choose whether if you want to import the whole geometry from a step file or any other CAD file, or you want to design it from scratch inside the software. In this project, as we designed the whole geometry previously in the CAD tool, I will import the geometry from the Explorer window. You can import different file extensions like Autodesk Inventor file, step files, SolidWorks files, IGS files, and other different CAD files into the software. For example, I will import this surface mounted magnetic gear file to the environment, and you will see all the parts are imported here. It is the outer region. I hide it. It is the band of rotation. I will right click on it and click on visibility to see the geometry of the simulation. To have a better view, you can rotate the geometry with holding the shift button and a scroller of the mouse. If you want to change the appearance of part, you can select them like this with holding the control button, and from this window you can change the appearance of that part. For example, I will choose these magnets to set them as red color, and the other set of magnets to be painted by blue color. The next step of the simulation is choosing the analysis type. You have to right click on analysis, go to the study, and choose the right study type for this project. The magnetostatic, AC magnetic, and transient magnetic are three different solution types for magnetic simulation, and we have three other for electrical field simulations. The magnetostatic will simulate the geometry only in the steady state, and you're able to only use the DC currents and voltage as excitation, and you cannot model the motion as it is a time variant parameter. The AC magnetic will simulate the geometry with pure sinusoidal waveform as input, but the most comprehensive analysis type is transient magnetic, because it will allow us to use the motion coupling, different waveform for excitation, and time variant parameters. So I will select the transient magnetic to set the properties of this analysis type. First, we have to select the name of analysis. In the solution parameters, the default values for iterative solver, residual error, and symmetry factor will be good enough. And the important part is a start time, end time, and time increment. You should choose the end time as 1 or 2 cycle of the rotation, and time increment is important because with a large time increment you will not see the curve diagrams. The software will only simulate the magnetic distribution in the selected time increments. So I will choose 250 microseconds as a time increment to have 40 steps in this 10 milliseconds end time. As I want to see the core loss too, I have to check this box for core loss parameter calculation and set the period of the core loss. In the advanced properties, there is option for HPC parameters to select the maximum logical cores to use. In many softwares, you have to pay extra for HPC licenses, but in the EMWorks, you can select up to 32 cores without any additional licenses. Let's select OK, and you will see the analysis tree is built here. We have these 5 settings to be set before the analysis to be able to extract the results: material, boundary conditions, excitations, forces and torques, analysis coupling, and mesh settings. After this straightforward workflow, you're able to analyze the simulation and extract the results. Let's start with setting the material. When you open the material part, you will see different bodies that you created or imported inside. As I know, all the magnet materials are the same and they are neodymium. I will select parts related to the magnet, and by right clicking on it, you have to select a material. When you click on apply material, the material will be opened. Here you will find materials categorized by the property, and in the material, search for N52 as the neodymium iron boron magnet created by ABM Magnetics. When you select the magnet, you are able to see properties of the material, like the relative permeability, remanence, and coercivity. If you need to change them, you can do it by clicking on Apply Material, and again, in the material part, you can right-click on each part and edit material. In this window, all the properties can be changed due to your material characteristics. I will leave them as default and go to select the inner yoke, modulation rings, and outer yoke. Let's select them. I selected all of them, and by clicking on Apply Material, again in the Material Center, first select the default library to search the whole library, and I want to use M300 because it is a material that the core loss coefficients and the BH curve is set by the datasheet of the producer. Let's click on Apply and Close. And again, for outer magnets, the same material, neodymium iron boron magnet, will be selected. I will select all of them, and by right-clicking on the parts, if you want to apply a new material, you should click on Apply Material. But if your material is used in the simulation, you can find it under the project folder. I will select N52 again, and the magnets are defined completely. The only remaining part is the band that covers the rotor and rotor magnets and the region. Both of them are air, so I will select them, and from the favorite material I can find air under default folder. The material setting is finished, but we need to set coercivity direction for permanent magnets. The coercivity direction will show how magnets are magnetized. So for all the North Pole magnets that are attached to both outer rotor and inner rotor, I will select the coercivity direction by right-clicking on them and choose this option, coercivity direction. In the properties of this coercivity direction, you can select the global coordinate system or local coordinate system. For this project, I will use the global coordinate system with cylindrical type. Inside the cylindrical direction, I will choose along R with the positive direction. For the South Pole, we just need to select the same properties with checking this box, reverse direction. Let's do it together. I will hide these North magnets and select all the parts that are related to the South magnet. Open the two folders, select them by holding the control button and clicking on coercivity direction. Again, the global coordinate system with cylindrical along R with reverse direction. The magnetization direction setting is finished by selecting the coercivity direction. The settings of the material part is finished like this. About the boundary condition, you can select normal flux or tangential flux if you have any special circumstances. But for a 3D simulation without periodic boundaries, you don't need to set boundary conditions. The outer air will be the biggest part that will be meshed and solved. The next part is excitation, when we can select the solid coils or wound coils to excite the geometry with current or voltages. But in this magnetic gear, we will not use the external excitation. Both outer rotor and inner rotor as permanent magnets, but this option will be very useful for simulating motors, transformers, actuators, and any electrical machine that use the windings. In the forces and torques, we need to define torque on inner rotor and outer rotor to be able to measure the produced torque in each part. So I will choose the virtual work, and in the properties page you need to select all the parts that you want to measure torque on them. We will name the first one as outer torque and select the outer yoke and its magnets. After selecting all magnets, you have to choose to calculate the torque at the origin or at any other point. And click on OK. We'll do the same for two virtual work. Name is inner and select the inner rotor part, the yoke and 8 and click on OK. The force and torque setting is finished. In the analysis coupling, we can select coupling, thermal coupling, and motion. For this simulation, we have one band and we want to set the motion coupling. So I will right click on the motion and choose if it is translation, motion, or rotation. In this project, we have rotation and motion, and in the prop, we need to select the components of motion, the band component, and set the direction and speed of the rotation. For moving component, I will select the rotor and 8 magnets on it. And for the band, we need to unhide the air that we selected for the band by clicking on Show and select this part as the band component. In the motion setting, we will choose to rotate around global coordinate system with Z direction. As we don't have any limit on the rotation, we will not check this box. In the last step, we have to select the initial angle, which is not important in this project, and the velocity. Due to the design, I will select 270 radian per second, but you can select different speeds by choosing different values of degree per second or converted to the RPM. Click on OK, and the motion coupling is created here. The last step in pre-processing is mesh settings. Let's hide the band again. Check the mesh operation. If you right-click on the mesh, you can create mesh by default or select mesh control to set more precise mesh on each part. Let's check the default mesh to see if it is enough. We will continue. Or if it was too big, we can select the mesh control to change the sizes on important elements. By clicking on the mesh, you will go to the properties of the mesh and you can select default values or change them to increase or decrease the mesh size of each element. By clicking on OK, it will start to mesh the geometry and show mesh elements. Let's check the mesh size in this mesh plot. As we can see, we have at least 5 or 6 layers inside the outer rotor, 3 or 4 layers for the middle steel, and good amount of layers inside the inner rotor. So even the initial mesh is good enough for this simulation. Now let's go to the hide mesh, and I analyzed the whole simulation to get the results. We can extract 2 kinds of different results from the solved simulation: the tabular results and field reports. For the tabular results, you can double click on the result table and in the opened window, select the time and the parameter that you want the value. For example, I will select some time step and check the forces, torque, losses, displacement, velocity, and core loss inside different parts. To plot them completely on a single diagram, you can select, for example, T around Z for both rotors and add them to the parameters to plot and create a plot parameter. You will see both diagrams in a single window. You can directly export this diagram to picture with different file extensions, or you can export the table to be analyzed in another software. You can export the whole values to the Excel file using the save option. The extensions like Excel file and CSV file available. Result: you can compare the primary and secondary or inner rotor and outer rotor torques. The maximum value of virtual work 2 is of virtual work 1 is almost 100. So the ratio 1 to 6 can be seen here. Of course, in actual machine, both inner rotor and outer rotor will rotate. But in this simulation, we only defined one band to see the torque characteristics of this geometry. Each of these points can be an operation point. For example, if we choose a phase shift between inner rotor and outer rotor, we will not get any torque like this point. The both torques will be zero. But with diff between these two rotors, we can extract the maximum torque to 600 Newton meter with the ratio of 1 to 6. So from this simulation, we found out the maximum available produced torque. Results like core loss in different elements will be plotted here inside the table of results, or you can go to the results center and view different available diagrams inside the results center, like the energy forces, torque, losses, displacement, velocity, core loss, and the plots will be generated automatically inside the results center. The other kind of results are field reports. We can plot magnetic flux density, magnetic field intensity, applied current density and generated current density inside the parts, loss density and force density. With clicking on each of them, you will see available options like 3D fringe plot, vector plot, or 3D streamline plot. I will choose the fringe plot without any clipping, with no clipping. It will shows the field distribution on different parts of the geometry. If you want a section in plot, you can choose section clipping, or from the top menu, use section view. This option is very useful because without drawing additional surfaces, you can plot the field distribution on any cross section of the geometry. I can select different to plot the field on them, and this plot is available on all field reports like the magnetic field intensity, applied current density, and other field outputs. Let's change the plane and try different view angles. This plot was magnetic flux density fringe plot. Let's draw a 3D vector plot with section clipping. With this section vector plot, you will see magnetic flux pass inside any cross section. You can select the viewpoint of the plot, and by selecting this timer icon, you can select the time step of the plot. If I click on the next field step, you will see the inner rotor position is changed. Depending on the simulation, different field plots will be useful for extracting results and watching the operation point of the machine. Thank you for your attention. Now we will start the questions and answers part. Hello all, please write your questions in the chat box and we will answer them one by one. Okay, the first question was about what determines the gear ratio in a magnetic gear. Just like the mechanical gears, the ratio of the gear will be determined by number of magnets in mechanical gears. The ratio will be determined by number of tooths or the circumferences of the circles. But in magnetic gears, the gear ratio will be determined by ratio between number of pole pairs between the inner rotor or outer rotor or low speed or high speed. The next question is about can you describe what are the main design trade-off in magnetic gear design? In magnetic gear design, like any other kind of uh, machines, the torque density or power density is the main issue. So we have to design a magnetic gear with the smallest size and uh, the uh, lowest production cost. So using high efficiency magnets, strong magnets, will increase the torque density, but it will increase the uh, cost and demagnetization risk. The other one was the air gap. You have to minimize the air gap, but it will have some issues, mechanical issues for tolerances and production cost again. And the other one is we can use different pole pairs for gear ratio, but the torque ripple and of course again the production cost will affect our decision. The other question is in an existing magnetic gear design, how can torque ripple be minimized? For minimizing the torque ripple, just like other machines, we can use the SQ angle in the rotor, in the inner rotor or outer rotor, or even in the middle ring in the modulation ferromagnetics. And the shape of magnet itself, with creating curved edges or offset in the magnets, we can reduce the torque ripple. And again, pole pair combination will affect the torque ripple. In the same gear ratio, different pole pair combinations will increase or reduce the torque ripple. What limits the maximum speed of magnetic gear? The magnetic gear does not have any intrinsic synchronous speed or maximum limitation of speed, but some parameters will limit the speed, the maximum speed. First is mechanical stress on the magnets, especially for surface mounted magnets. The centrifugal forces can cause some problems in the high speed rotor, and the losses, eddy current loss in the field modulators or even the magnets will make some problems in heating. Core loss will increase the temperature of the system, and we have always problems with the temperature. Demagnetization risk will be increased in higher temperatures. These are the limitations of the speed. The last question is, thank you very much for your kind message. If you have any further question, we will provide a form for you to ask your question and leave your email there. Our our engineers will contact you to consult and give you more information about this webinar or any other projects. As we answered all the questions, here is the end of the webinar, but you will have the recorded version of the webinar on the YouTube. Feel free to ask your questions on the comments, and we will try to answer them all by contacting you. Thank you all, and have a good day.